How's it going, Rylan? Feel free to ask me any questions if you have them. We got about 4 minutes before class starts. Hey, Ethan, feel free to ask me any questions if you have them while we're waiting.
I'm just confirming the test is Thursday, right? Online.
Yeah, I'm actually it's going to be taken at your leisure. So basically, I'm going to make it available. I might even make it available as early as tomorrow, but definitely by Thursday it'll be available, and you'll have until I'm going to say basically till Wednesday of next week to get it done. But you have to use the if you have a webcam, then you can do it at home as long as you have a computer that can run Respondus lockdown browser and Respondus monitor, and you have a webcam. And then I also prefer you to have a mirror. You're not required to, but there's some probability that if you do it without the mirror, I might look at the video and say, no, I can't see enough, so I need you to retake it, at which time you could take it either with me or testing center or something like that. I hope that makes some sense to you guys. Still got about 1 minute. Ava, you have any questions? Or Bruce?
I actually did. I saw that the practice test was up. When will the online test be up?
I should put that up tonight or tomorrow. And you will have at least until Sunday at 11:59 to get that test done. What I would recommend though is since that test and the next face-to-face test are on the same material, is I'd recommend you take the practice test over and over as many times as you can. The ideal scenario is that you can consistently get an 80 or higher without having to Google any questions. And if you get like 3 or 4 in a row that are 80 or higher without Googling any, you're probably in a pretty good pace to take the test, at which time I'd go ahead and take the online test. And then as soon as you finish that, I would jump in and take uh, the face-to-face test, which is, with the lockdown browser and the Respondus monitor.
Okay, thank you.
You're welcome. You do get multiple attempts on the lockdown browser one, on the online test, but on the lockdown browser and lockdown monitor, Respondus monitor, you're only going to get one attempt on that. So just to specify. Anybody else have any questions? All right, well, it's time to get started. This is not really as many students as I hoped there would be, but I'm going to go ahead and get started anyways. Let me start off by doing the roll thing because I still ain't found my roll sheet. So I'm taking a screenshot of the roll sheet each day. And that hopefully is enough to keep track of it until I can find my roll sheet. Okay, let's see, 242. Okay, today is July 2nd. I've got that. Okay. So last time we finished chapter 23, and by the way, I did notice that many of you finished chapter 23 by 7:01, which is great. I did record that. I'm probably going to give those of you who finished it some extra points because I literally remembered going in and setting that date a little later than what it was, and it didn't take or something. So I felt bad about that. So those of you who did it, I'm going to give you a couple extra points, but those of you who didn't do it, I've already set the due date back further, and therefore you can get it done and chapter 24 done. I think they're both due on Monday of next week. But either way, I did set those dates back. And those of you who worked really hard to make sure you got it finished by July 1, which was the original deadline, I apologize. I thought I had changed it, but clearly I missed something. So please make sure you get that done. But the people that already did get it done, I'm going to give you a couple extra credit points just for doing it ahead of time. Once the student gets in, I'm going to re-explain that really quickly. It looks like Sebastian's in now. Okay, so what I've just finished telling everybody, Sebastian, since you just got here, I want to let you know that the online test should be coming available tonight or first thing tomorrow. You have, or sometime tomorrow, you have, I think what I decided was until for you guys Monday, it's Sunday or Monday night at 11:59 p.m. to get that online test done. I've decided to go a little longer on the face-to-face test, which covers the same chapters. So really you have the same practice test for both of them. And that online test, the face-to-face one, will be held online, but you'll need a webcam. You'll need a computer that can run Respondus lockdown browser. You need a computer that can run Respondus monitor, and you need a computer that can run Canvas testing. And you'll need a mirror so that you can make it look like the non mirror placement photograph that I have in documents and links. If you don't have that, you can still take the test on your own at home, but there's some probability that if I look at the video and it looks like you might be focused a little down below the desktop or up over here, you're staring off into the distance over here or over there, somewhere that I can't see because I don't have the mirror or well, mainly because I don't have the mirror, then I might ask you to take it again and you'll be required to take it again. Not as an admission of guilt or anything like that, just because it was insufficient. That can be done either at the testing center or there's times where you can come in and do it with me proctoring and stuff like that. So you don't have to go out and buy a mirror. If you have a mirror that's like 10 by 12 or something like that, that would be ideal, or a full length mirror. But in principle, it'd be like you have the desktop monitor right here, you'd have the mirror here, and you'd be sitting here so that I could, in principle, look through the webcam into the mirror and then see your workspace and see, you know, if you had anything on your lap, I could see that. If you had anything back behind your monitor, I could see that. And I could see actually where you're writing down and solving problems and, you know, filling out your scratch paper, that kind of stuff. That's what the actual mirror is for. But again, I don't think you guys are cheating or anything like that, but I have caught people, so that's how I have to do that. Okay. Anybody have any questions? So keep an eye out. I will put all that information regarding when those tests are due and that sort of stuff. That will be in an email that I'll send to everybody. So you should be able to see it in writing and not have to just remember. but do make sure you don't miss the deadline for test one online, or excuse me, for the online test, as well as for the face-to-face test. You got 2 tests coming up. One of which, the online test, will be due either Sunday or Monday. I can't remember what I set it to, but I think I planned on doing it Monday at 11:59 p.m. And the face-to-face test was supposed to be due at the same time, but now I'm allowing, because the testing centers won't have Friday after July 4th or Saturday after July 4th. They're not going to have that available. So I'm pushing it to at least Tuesday, but maybe even Wednesday as a day that you're allowed to do the face-to-face test. Okay. So no questions on any other material or anything like that, because I'm getting ready to move on to chapter 24. Okay. It looks like we're good to go. I've got the chat window up, so if you type something, I can see that. If you don't, of course, you can also just speak out and I'll hear you. Both of those are fair game, so do any way you can to get a hold of me. And remember, guys, I feel like a lot of time with you, it might be that you guys are actually following me pretty well, and I hope so. That's great. But if you feel like I'm just sort of steamrolling you and just talking over and getting all this stuff to you but not really teaching you, then you need to stop me, because I don't want that. I want you guys interacting with me. I want me to ask you questions and you to think about the answers, and you don't necessarily have to blurt out the answer, but if you're not doing that part, you're probably not learning as much. So I definitely want to make sure you guys are trying to stop me and ask me questions if you don't understand something. Today I'm going to be doing something that I consider one of the major paradigms of the course. There's a few things for instance, in calculus-based physics that everybody should be able to do. Obviously, the lowest hanging fruit is being able to add vectors, multiply scalars by vectors, take dot products of vectors, take cross products of vectors, that sort of thing. But the next echelon of that is performing path integrals and line integrals, which is what we did when we first discovered work in chapter 7, and doing surface integrals, which we did when we first covered Gauss's law, and specifically this paradigm, which is where you can take either Coulomb's law in integral form or Gauss's law in integral form and use that to compute an electric field. Then you use that shape that you used to create the electric field and then calculate the electric field that was that you determined from it. You use that to form a type of capacitance. Now, it could be a parallel plate capacitor, which has 2 plates that are parallel like that, and they're supposed to be so close together that they're really the center of it's really far from the edges, and that creates a uniform electric field, and that's called a parallel plate capacitor. But it turns out you can also find that there's a capacitance in coaxial wires or in concentric spheres. So you should also be able to use Gauss's law or Coulomb's law in integral form to compute the electric field between the inner and outer wires of a coaxial cable, or between the spherical concentric spheres. Okay. Once you've done that, then you have to use V equals a negative integral of E dot dl to calculate the voltage difference between the 2 parts of the capacitors, which would be the positive part and the negatively charged part of the parallel plate capacitor, or the coaxial cable, or the concentric spheres. And then finally, you're supposed to use C equals Q over V to calculate the capacitance. That's the 3-step process: using Gauss's law or Coulomb's law to calculate electric field, using V equals negative integral E dot dl, and then using C equals Q over V. That's a 3-step problem that I'm calling a paradigm that you guys should be able to do. When we get into magnetism, there's going to be another paradigm where you use basically the definition of magnetic flux, and you use the either Ampere's law or the law of Biot-Savart to calculate the magnetic field, and then you use that flux definition to calculate the flux, and then you use the inductance, which is called the self-inductance, a formula for that to calculate the actual inductance of these various shapes for inductors. That's another paradigm. Both of those are critical to you completing this course. So I'm going to work it that way. I'm going to rapidly blow through Gauss's law and then putting everything together, so you'll see more examples of Gauss's law. So keep that in mind. You are supposed to be able to start from Gauss's law or Coulomb's law and determine electric field, then use V equals negative integral E dot dl to calculate the voltage difference, and then use C equals Q over V to calculate the actual capacitance. So we're going to start off by referring you to your textbook. So let me do this with the share screen. I'm going to share screen and we're going to open up your textbook, which is right here. And this is actually in the section that I'm not that not there yet. Okay, so here's a picture of various capacitors. Okay, last time we covered chapter 23, we talked about electric potential and we talked about electric potential of a dipole. And then chapter 24 is about capacitance, dielectrics, and electrical energy storage. And a capacitor is something that can store charge. That's one way of looking at it. But a more robust and helpful way is thinking that a capacitor is something that can store energy. And it can deliver the energy either lightning fast or really slow, depending on how you set it up. In that sense, it's actually better than a battery, because a battery, you only have the choice of a battery putting out as much power as it can based on the device that it's attached to. So a battery can often discharge very slowly, whereas sometimes you want a big release of energy all in an instant. If you want that, then you need a capacitor as opposed to a battery. In this case, you see those little blue and yellow and black and yellow, or excuse me, blue. I don't even see yellow on there. I don't know where the color yellow came from. Do you see the blue and the Carolina blue, or the blue and the light blue cylinders? Those are very typical capacitors. Also, if you look down here, these look like black and blue capacitors. They're very typical capacitors. They're cylindrical. They have two terminals sticking out of them, so you can't see them here because they're all in such a way that you can only see one of the little legs. But there's two little legs sticking out of this one, there's two little legs sticking out of this one, there's two little legs sticking out of this one and this one. And it turns out this guy right here is probably also a capacitor. The fact that it has that Z on it makes me think that it might just be a diode, but I'm pretty sure it's still a capacitor. They often look like this, and they often look like that little round puffy thing back there. This is another capacitor. Basically, cylindrical is the more natural thing, but they always have two terminals, and they might be a little puffy. The simplest case of a capacitor is two parallel plates, one charged positively with a charge of positive Q, and the other one with the exact same charge but negative. So those two plates next to each other make what's called a parallel plate capacitor. And I'm going to show you that the capacitance in that is directly proportional to the surface area of the plates and inversely proportional to the separation between them. So if you want really high capacitance, you want a really big area or a really small separation distance. Once you make something like that, if you had some way of sticking something between the plates, that's a non-conductor. A fancy word for a non-conductor or for an insulator is a dielectric, and that's where that word came from that you're seeing in the chapter title. But if you put a dielectric in there, that actually gives a physical support to the two plates that keeps them apart. And being a non-conductor, it makes it a little harder for basically charge to jump, say, from the positive plate to the negative plate, which is the failing of the capacitor. So it aids in that, but it also aids in mechanically keeping the two plates apart. Therefore, you can, for instance, fold up the plates and then roll them up really small and fit them into a little cylinder like that. Okay, so that's a lot of how they do it. And sometimes the two conductive plates are just literally sheets of mylar. And then the sheets of mylar are separated by let's say a little crystal of silicon or something like that, or a little wafer of silicon between them, or even a wafer of something that's even more malleable so that you can roll them up. Now that we have that, I'm going to go ahead and stop sharing this screen, and I'm going to share my iPad screen. So sharing my iPad screen. doing that right now. And now I'm telling my iPad to share it with my computer, and that should come up in a second. So Alessandro Volta, who gave us our first battery, basically, he came up with an expression for this quantity that they had discovered as capacitance. And he said, we're going to define the capacitance to be the charge divided by the voltage. So anything you can imagine that could actually store charge. So he used to use something called Leyden jars, Leyden jars. You could build up charge on them, but the amount of charge that you put is largely dependent on how much voltage you could put across it. So they found out that the best thing was to divide the charge by the voltage, and that gave them a quantity that was usually just a geometric calculation. In other words, that capacitance shouldn't have anything about the charge density or about the total charge in it, but it will have geometric factors like the distance between them, between the plates, or the area of the plate, stuff of that sort. As you can see, the formula C equals Q over V tells us that the units for the capacitance are coulombs per volts, and of course a volt is a joule per coulomb. So that also gives you coulomb squared per joules. That's another unit. But in principle, that coulomb per volt or coulomb squared per joule is also defined to be 1 farad, F-A-R-A-D. Notice that's short for Faraday, and that's what it's named after. And the abbreviation for a Faraday is a capital F. A farad, or excuse me, abbreviation for a farad is a capital F. And a farad capacitor is a really big capacitance. 1 farad capacitor could really kill you, for instance. And in fact, when you have capacitors lying around, you're supposed to connect the two terminals with a conductor so that charge will just accumulate on it. The reason being is, for instance, imagine you had a 1 farad capacitor, a 1 farad capacitor laying in a room. Just from the air and moisture and stuff like that, you could actually accumulate charge on that capacitor over time. And the capacitance being 1 farad could allow a lot of charge on there. If I happen to walk up and inadvertently connect the circuit between one of the terminals of the 1 farad capacitor and the other, that could lead to a current big enough to kill me. So you keep them basically connected together so that charge don't connect on them. So that's part of the problem of having a 1 farad capacitor, is it holds so much charge that it can deliver quite a shock. So what we're going to do now is we're now going to use that formula C equals Q over V and these other formulas to show you the paradigm of calculating capacitance. So here's the paradigm that I've been pointing to. I'm going to start off with this example. It says use Gauss's law, C equals Q over V, and delta V equals the negative integral of E dot dl to compute the electric field near an infinitely large uniformly charged plate of area charge density sigma. So we're going to assume the charge distributed over the area of the plate is sigma coulombs per square meter. And do that in doing that, I'm going to then imagine 2 of such plates oppositely charged, very close to each other and parallel to one another, and use Gauss's law result that we just got to compute the voltage difference between the 2 plates. Then we're going to take and use C equals Q over V to determine that capacitance. So let me show you what I mean. So first off, what we're imagining is that we have an infinitely large plate, which really just means a plate that is going to be, we're going to be so close to this plate that if I wanted to find the distance from where I'm calculating the electric field to the edge of the plate, then I want to be able to multiply the distance from me to the plate by 10 and still get a number smaller than the distance away from the edge. That's sort of the hard, steadfast rule. in principle, I would say I would prefer a factor of like a 100, but a factor of 10 would be enough. Okay. Sorry, I didn't realize my friend's out trimming my bushes. I was like, who the heck's cutting my trees down? But a friend that's staying with us just went out there and I didn't recognize her until then. So anyways, that's what we're going to do is imagine these plates where I'm going to calculate an electric field close to it. Okay. And again, meaning close, meaning that if I'm 1 centimeter away, then I have to, and I want to calculate the electric field there, then the side must be at least 10 centimeters away from me, but I'd prefer 100 centimeters. So that's what I'm going for. This is going to be my x-axis. This is going to be my y-axis, and this is going to be my z-axis. And what I'm going to do is imagine the plate as technically being really, really large, but I'm just going to draw it right here like so, and just say it goes on forever that way, and this way, and this way. And when applying Gauss's law, there's really just three shapes that we use when we're applying it to solve for the electric field. The shapes are a cylinder, what they call a Gaussian pillbox, or a sphere. Okay. Now, in the case of a cylinder, there's two ways you can use it. There's a way you can use it where it's like I'm always going to refer to it like a soup can, but in the case of the soup can, one way of using it is that the lid is going to have an electric field that is constant and perpendicular to the lid on the top and on the bottom. That's one way we could use the soup can slash Gaussian pillbox. Another way we could use the soup can slash Gaussian pillbox is where the electric field is a constant on the soup label and perpendicular to the soup label, but at the top and bottom, the electric field can vary quite a bit, but luckily the electric field is perpendicular to a normal vector to that top or bottom, so that contribution turns out to be zero. So just keep that in mind. That those are the two shapes that you can use, either a cylinder, which is like a soup can, or a Gaussian pillbox, or a sphere. So can anybody tell me, if I'm trying to calculate the electric field some distance z above the xy plane, because the actual plane of charge, which has a charge per unit area sigma, that's actually in the xy plane. So do you think I'll be using a spherical Gaussian surface, or would I be using a soup can Gaussian surface? So with this plane, I'm trying to imagine a Gaussian surface, and Gauss's law says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. I'm trying to do that left-hand side. The left-hand side is supposed to equal just an electric field times an area, and maybe some other terms that are also electric fields times area are zero. In order for them to be zero, then the electric field has to be pointing perpendicular to the dA vectors, or the electric field has to be zero or something like that. And in order for us to get an electric field times an area, the electric field has to be constant on a surface, and therefore the electric field has to be parallel to the dA for that surface. Okay. So for this plane that I'm showing you, will we need to use a sphere to find a surface on which the electric field is constant, or will we need to use a cylinder or a Gaussian pillbox, that is, to find a surface on which the electric field is a constant? Anyone? All right, I'm not getting a lot about. Did someone get ready to say something? Oh, someone might have chatted. I just see a chat popped up. Maybe it popped up. Soup can. Yes. Very good, Ethan. Thank you. Yes, it's a soup can. And here's my argument for it. If you imagine parallel to the, let's say, y-axis, you could have a particle right here, okay? And then right above it, which is where we're trying to calculate the electric field will point straight up. But just to one side of that, you're going to have another particle that's identical to the first one, and that's going to cause an electric field that points that way. And then you'll have another one over here that's going to cause an electric field that way. So from that reasoning, you should be able to tell that the center charge is going to cause an electric field pointing up. The charge over here is going to create electric field pointing up and to the left, and the one over here is going to create an electric field that's pointing up and to the right. So the left and right components are going to cancel each other out, and you're only going to get electric field pointing up. So that means that we shouldn't have any y component of the electric field. Now, what about the x component? Well, the x-axis is in and out. So imagine a particle here, and then a particle behind it, and then a particle in front of it. The same thing happens there. The middle particle creates electric field pointing up. The back particle makes an electric field pointing up and forward, and the forward particle makes an electric field pointing up and backwards. So the backwards and forwards components cancel each other out. So that tells you it also shouldn't have any x components. So at least above the plate, we expect the electric field to point up. Below the plate, we expect the electric field to point down. And in fact, by the symmetry of it, we'd expect a surface parallel to the plate is going to have a constant electric field on it. So with that in mind, my Gaussian surface is going to be a soup can that actually penetrates through the plate and sticks through on the other side like this. So that we have essentially, if I zoom in on this like that, there's my, and notice I left it like that so you can see that that's going back behind the z-axis. And this is also down back below the frame and the plate that we're talking about. Now, what that's going to have is a little differential area element dA, which is going to be dA k hat. And down here, we'll have a similar area, and that dA, which I'll call dA bottom, is going to be negative dA k hat. Whereas this one, where this one was dA top. Now, this guy over here is also going to be a dA. I'm going to call that dA soup label. And that's going to be a dA times some n hat, which is just a vector that only has x and y directions. It doesn't have any k hat component whatsoever. Okay. We could call that, for instance, the r hat from polar coordinates, and that would be fine. But I just wanted to get an idea of exactly what we're doing there. So now I can say left-hand side, and that's equal to the closed integral of E dot dA. And in this case, we're making a hypothesis, so I'll go ahead and do that. That E is equal to some positive E of Z k hat for Z greater than 0, and some negative E of Z k hat for Z less than 0. So what I'm going to get is the integral over the top plus the integral over the bottom plus the integral over the soup label, which is going to be the integral of E of Z k hat dotted with dA k hat integrated over the top plus the integral of negative E of Z K hat dotted with negative dA K hat. And that's over the bottom, plus, in this case, we're going to say plus or minus E of Z, because I got to go up and down the whole soup label. So from above the plane where the electric field is positive E of Z K hat to below the plane where the electric field is minus E of Z K hat. And then all this is going to be dotted with dA N hat. And this is over the soup label. So when I do that, what I get is for the top, and actually I should probably not put that. Yeah, I'm not going to put that equals there because you might get confused about what it means. So I'm going to say the left-hand side is equal to, and I'll put it right here. What this becomes is, since we're on the top of the soup can, the Z is a constant. So E of Z has to be a constant. And I'm going to say E of Z times the integral of dA times K hat dot K hat. And this is the integral over the top. Plus, notice the two negatives, the negative E of Z K hat and the negative dA K hat, make a positive E of Z. Again, this is the bottom surface and Z is a constant. So that integral or that E of Z is a constant, and it comes right out. And I get dA K hat dot K hat. And then the other one is integral plus or minus E of Z dA. And then this one's K hat dot N hat, but K hat dot N hat is 0 because K hat points in the positive Z direction, whereas N hat has no Z component whatsoever. So when I actually do K hat dot N hat, it'll be some number times K hat dot I hat. That's 0 because the I hat and the K hat vector are differ by 90 degrees. So the cosine of 90 is 0, so you get 0. Additionally, when you do E dot dA, you get E of Z again times, in this case, it's going to be K hat dot J hat, because the N hat can also have a J hat in there. Well, the J hat again is also differed by 90 degrees. So the cosine of 90 gives a 0. So we get a 0 for that. And ultimately what we get for this part is just 2E of Z. Now the area of the top is going to be equal to the area of the bottom of the soup can. And I'm going to say that that area right there is just A. So what that means is now I'm going to get 2 times E of Z times A is the left-hand side. Now, the right-hand side, and that is Q enclosed over epsilon naught. In this case, when we look at it, notice basically that the whole bit of charge right here, actually, let me do this in purple. The only charge enclosed inside of this soup can is the charge in that area A. And since the charge density in dq over dA is sigma, then all I have to do is multiply sigma times A to get the charge enclosed. So that's what the next side is going to be. So now I can write this as sigma A over epsilon naught. Then I can say left-hand side equals right-hand side. And this gives me 2E of ZA is equal to sigma A over epsilon naught. And that tells us that E is equal to E of Z, or excuse me, I forgot. I was writing the original hypothesis, but we now know what E of Z is going to be. E of Z is going to be sigma over 2 epsilon naught, and then it's times k hat, and this is for Z greater than 0. And then we're also going to have a negative sigma over 2 epsilon naught k hat for Z less than 0. So that's what Gauss's law gave us for the electric field. Now I'm going to imagine, and this goes on a ways this way, I'm going to imagine a charge of plus Q for this plate and a charge, again, it can go on for a long way that way, of negative Q there. Okay. And what I have to do is consider, let's make the positive plate look as if it's purple and blue. And then I'll say at this point right here, the electric field due to the positive plate is pointing to the right, and its value is sigma over 2 epsilon naught. Now the negative plate looks attractive to a positive charge, so the positive charge is going to want to go to the right as a result of the negative plate as well. So in this case, I'm going to say the negative plate gives me a electric field of sigma over 2 epsilon naught as well. So the net electric field inside is equal to sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which equals sigma over epsilon naught. Now, out on the each side, we already shown before that E equals 0 and E equals 0 out here. And that's because the positive plate and the negative plate point in different directions outside. Now that we have that, we can now say that the electric field inside of the plate is actually equal to, let's put a vector symbol on it, and now I'll just put a k hat after it. Okay. And I'll put this in parentheses and put a k hat here as well, just to make it consistent all the way across. So everybody now sees that I was able to use the result from Gauss's law, sigma over 2 epsilon naught, to find the total electric field between the plates. Now, the next step of the paradigm is using V, or delta V, is negative integral of the conservative electric field dotted with dl. So this becomes, I'm going to set it in an actual coordinate system so that we can do it, but I'm going to say, for instance, that this, that this black line right here is the y-axis. And I'm going to say that this is the x-axis and this is the origin. And I am going to integrate from here to here. I'm going from the negative plate to the positive plate, in other words. Okay, because that delta V would be from a low voltage to a high voltage. So final minus initial would give me a positive quantity. So I'm going to put my negative here because that's part of the formula. I'm going to take the integral. Sorry about the dogs. I'm going to take the electric field, which is sigma over epsilon naught, and it's actually pointing in the right direction, to the right, in other words, and I'm going to say that's in the I hat direction. So there's my conservative electric field. Now I've got to dot that with the DL. Now remember what I told you about path integrals. You've got to either choose the DL to point the direction you're integrating or choose the range of integration, but not both. This time I'm going to choose the DL. So I'm going to say that I'm actually integrating in the negative dx I hat direction because I'm going from x equals 0 to x equals negative d. In other words, I'm specifically going to call this distance from here to here is going to be D. So on the x-axis, this would actually be a negative D. So by doing that, I'm now required to just point the range of integration in the positive coordinate direction. So I'm acting as if I'm integrating from 0 to D, when in fact I actually am going from 0 to, excuse me. Let me fix that. I'm actually going from 0 to negative D. So the positive coordinate direction would be negative D to 0. Okay, because negative D to 0 is to the right, which is the positive x direction. So now you can see that the two negatives, the negative dx and the negative out in front, are canceling each other out. And I'm going to get the integral from negative d to 0 of sigma epsilon naught dx I hat dot I hat. And of course, I hat dot I hat is just the magnitude of I hat, which is 1, times the magnitude of I hat, which is 1, times the cosine of the angle between the two vectors when they're tail to tail, which in this case is 0 degrees. And this all gives me 1. So now what I get is a sigma over epsilon naught times the integral of dx from negative d to 0. So this is going to give me sigma over epsilon naught. The integral of dx is just x. When I evaluate x at 0, I get 0 minus, now I evaluate x at negative d, I get negative d. And you can see that I ultimately get sigma d over epsilon naught. And it did come out positive, okay? Now, this is really good practice to make sure you do it right. You actually put in the direction of the electric field, and then you integrate from low voltage, which would be the negative charge, to high voltage, which would be the positive plate, and you should come out with a positive value. That being said, if the voltage comes out the negative, just erase the negative sign and use it, okay? So, should come out positive, but you're going to go ahead and make it positive no matter what, rather than waste steps. So now I've done part 2 of the paradigm. Part 1 was computing the electric field using Gauss's law or Coulomb's law, usually Gauss's law. Part 2 is using delta V equals negative integral of E dot dl to find the voltage difference between the two parts. And now part 3 is using C equals Q over V to compute the actual capacitance. So what we know is Q is sigma times A, and what we know is V is sigma D over epsilon naught. You can see, in fact, that the two sigmas cancel out, and we ultimately get that the capacitance is epsilon 0 times A over D, and that's actually correct. The capacitance of a parallel plate is just epsilon 0 A over D. Now, that is a result that is listed on your equation sheet, and it's one you're allowed to use. But if I specifically ask you on a exam or test, obviously not this one, because the one that's coming up is only up through chapter 22. So it requires you to know Gauss's law, but not computing voltage nor computing the capacitance. Okay. So you can use that formula over and over again, and that's certainly fine. Now you've seen how the paradigm works, as well as know the formula for capacitance. Now, if we were to put a dielectric in, if there was a dielectric between the plates, then C would equal K epsilon 0 A over D, where K is the dielectric constant. And I wanted to write that in a different color. So that's a quantity that your book has a table with various values in it. So you look up the material, find out what they put in there, you find out what the K is, and you multiply it. But another way we can do that is we can also write it as just epsilon. Notice I didn't subscript it. Epsilon A over D, where epsilon is just K times epsilon 0. So all of these are valuable results as well, and we'll make use of that as we go along, but I just wanted to give you that now. Anybody have any questions on that one? Now, I didn't do that as quickly as I'd like. You know, I tried to go back and explain Gauss's law again a little bit. The rest of these I'm going to have to do rapidly, like you're supposed to do when you're taking a test or doing homework or something like that. So I finished with that example. Now we're ready to do another example to see how we actually can use such a formula. So in this case, it's example 2. It says calculate the capacitance of a parallel plate capacitor whose plates are 40 centimeters by 3.50 centimeters. That's pushing the envelope about how big you can fold these things up and still make them small enough to put on a circuit board like the ones you just saw. But again, just letting you know, that's roughly what you could go up to. So we're actually going to have a 40 centimeter by 3.5 centimeter wide area, and it's going to be separated by 0.5 millimeter. That's really pushing the envelope here because at 0.5 millimeter, that's a little bit thinner than a typical staple is thick. So you can see that's a very small distance. That small distance means that little bit of air is the only insulator we got to keep lightning from striking from the positive plate to the negative plate, assuming positive charges move. It's more likely they're going to come from the negative plate and go to the positive plate. But the main thing is that's what we're going to try to avoid by putting the dielectric in there. So right now, when you see it's that close, you got a sense that, oh, since we learned that it's 3 million volts per meter is the breakdown voltage of air, then a single millimeter really only needs a voltage on the order of 3,000. In this case, it's 0.5 millimeter, so it really only needs a voltage of about 1,500 before it fails. All right, so now let's work on our solution. So we're supposed to be using Gauss's law, and then delta V equals negative integral of E dot dl, and then C equals Q over V. I'm going to start with the left-hand side of Gauss's law, closed integral E dot dA. In this case, it's the capacitance of, oh, no, sorry. This is a parallel plate capacitor. I forgot which example I was doing. Let me get rid of that part. Now, this part's really easy. What we're using is C, darn it. Not really. Okay, what we're using is C is equal to epsilon 0 A over D. And for part A, we want to know specifically calculate the capacitance. So in this part A, we're calculating the capacitance. That's going to be 8.85 times 10 to the negative 12th. Remember, that was Coulomb squared per Newton meter squared, which we could also write another way, but I'm leaving that off for right now. The area is going to be 40.0 times 10 to the negative 2 meters times 3.50 times 10 to the negative 2 meters, and then divided by the separation, which is 0.500 times 10 to the negative 3 meters, because that's in millimeters. Okay, centimeters are 10 to the negative 2, millimeters are 10 to the negative 3. So you can see now that the two centimeter measurements now converted to meters are going to cause the meters to cancel out with the meter squared in the bottom and epsilon zero. And then we're going to end up having a Newton meter at the bottom, which is a joule, but that's below coulombs squared. We did just show you earlier that coulomb squared per joule is the same thing as a farad. So we can now see that the units do work out, and it's going to become 8.85 e to the negative 12th times 40 e to the negative 2 times 3.5 e to the negative 2. And now I'm going to divide that by 0.5 e to the negative 3, and that gives me 2.478 times 10 to the negative 10th. And as I said, this came out to be coulomb squared per Newton meter, and a Newton meter is a joule, so that's coulomb squared per joule. This is actually equal to, what I'm going to do is, I know I have a 10 to the negative 9th as a nano, so that would be kind of helpful. So if I wanted to change this 10 to the negative 10th to 10 to the negative 9th, I would have to multiply it by 10, because 10 times 10 to the negative 1 would be 10 to the negative 9. But if I'm going to multiply that by 10, I've got to divide the 2.478 by 10 as well. So I'm going to call this 0.02478. And of course, the 8's not a sig fig, times 10 to the negative 9. Now we're making use of the fact that a coulomb squared per joule is a farad. So I can do like that. So I can actually call this 0.02478 nanofarads, and that's the capacitance. So that's part A. Anybody have any questions with that? Part B says, what is the charge on the plates when the capacitor is connected to a 12.0 volt battery? Well, that's easy enough. For part B, what we're supposed to do is B, we use C equals Q over V. So that means I want to know what is the charge. So I want to find Q, which is C times V. Well, we know the C is 0. Well, actually, I'll just stick to the original number. It's 2.478 times 10 to the negative 10 farads times 12.0 volts. That gives me 2.974 times 10 to the negative 9th coulombs, or Q is equal to 2.974 nanocoulombs. All right, that's enough. Calm down, dogs. We got a neighbor dog visiting us, and the dogs are going crazy. Everybody understand how I did the charge now? Anybody have any questions on that? Now it says, all else being equal, what area would be required to create a 1 microfarad capacitor? So that brings us to part C. And what we want is C equals 1.00 farads, which is also equal to epsilon 0 A over D. So really, when I say all else being equal, that's really just the epsilon 0 isn't going to change, duh, but the D is going to stay the same. So what I'm going to do is I'm going to say 1.00 farads is equal to 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared times area divided by 0.500 times 10 to the negative 3rd meters. And that gives us A is equal to 1 times 0.5 e to the -3 is 0.5 times 10 to the -3. Now I'm going to divide that by 8.85 e to the -12. And that gives me an area of 5.64, actually 6497 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th square meters. So you might not have an appreciation for how big that is, but to give you an example, it could be, for instance, 565 meters by, now that just took care of 10 to the 2. So now I still need times 100,000 meters. So 565 meters is like 6 football fields. So it's going to be 6 football fields times by 100 kilometers, basically. So you can see that a whole farad capacitor really takes a buttload of area, even with that small of a distance. But you can, in principle, once you put a dielectric in there, make the area even smaller, or excuse me, make the separation distance D even smaller. Now that happens to be just one configuration, 565 meters by 100 kilometers. Yeah, that works. That's 10 to the 4th, 10 to the 5th, 10 to the, that's 10 to the 5th, 10 to, yeah, okay. So that is one that works. It's not the only one, of course. You could, anything that multiplies to give you 5.65 times 10 to the 7th would be fine. Anybody have any questions on that?
Which one is the electric field? Because I see D as the area, but I'm not sure.
Okay, in this case, the electric field turns out to be just sigma over epsilon naught, but this one I wasn't asked to calculate that. But if we wanted to, I can say extra. What is the E field?
It's in the question, by the way.
Is it? Then I just completely forgot. Oh, yeah, it is. Thank you. I appreciate that. What is it? Yep. Part C. So this was actually part D. Let me correct that then. And let me get rid of the extra part. Thank you for fixing that for me. And this is part D because I screwed up and skipped a step. So here's part C. So part C, there's a couple ways we can do it. We can say we know for a uniform electric field that V is equal to E times D, in which case you'd say E is equal to V over D, which would be 12.0 volts divided by 0.500 darn it, times 10 to the -3 meters, in which case 1, 2 divided by 0.5 e to the -3 gives me 24,000 volts per meter. So that is actually one way we could calculate it. And of course, these two zeros are not sig figs. And I'm going to say this is E, and I will put a box around it and label this as C. Now, another way we could calculate it is E is equal to sigma over epsilon naught, and sigma is equal to Q over A. So if we calculate that way, we'd say 2.974 times 10 to the -10th. Oops, I wrote everything backwards. Or actually, no, I just missed a 9 for a 4. Okay, so this charge is going to be 2.478 times 10 to the negative 10 coulombs divided by an area, which would be 20.0 times 10 to the negative 2 meters. No, it's not 20, it was 40. Yeah, 40, sorry. So 40.0 times 10 to the negative 2 times 3.50 times 10 to the negative 2 times 8.85 times 10 to the negative 12th. And I'll just leave the units off there because we can still work it out. So I'm going to take 2.478 e to the negative 10, and I'm going to divide that by parentheses 40 e to the negative 2 times 3.5 e to the negative 2 times 8.85 e to the negative 12. And lo and behold, 2.478 times 10 to the negative 10. And I did want to make sure I did get the right area. That was 40 by 3.5. I did do that. 3.5 times 10 to the negative 2. I did do that. 8.85. 2.478. Sigma over epsilon naught. Did anybody calculate this? Oh, no wonder. I used the C instead of the Q. Stupid me. When I looked up here and saw the points, the 2.478 times 10 to the negative 5th, I was thinking that was the charge, but it was the capacitance. So that was me having a bonehead moment. It was coming out to 2,000 instead of 24,000, so I knew it was wrong. Now, if I correctly write darn it. If I correctly write 2.974, maybe I was actually right when I was copying 2.9 earlier. So it's 2.974 times 10 to the negative 9. Even that was what I wrote. So actually, that's what happened is when I thought I'd written it backwards, I just made a mistake in the middle of it. So I'm going to do 2.974 e to the negative 9 divided by parentheses 40 e to the negative 2 times 3.5 e to the negative 2 times 8.85 e to the negative 12. All of that's in parentheses, and lo and behold, I get 24,003.2 volts per meter. And of course, we said those last two digits were not sig figs, and the same thing's true here. So it is correct to the proper number of sig figs, namely 24,000 volts per meter is the size of the electric field. Thanks for catching me on that electric field, completely skipping that part. Anybody have any questions on that? Yeah. Remember that V equals ED. I've seen people use that in a lot of different ways. It's not that useful. Don't think it's that useful. That's only true when the electric field is a uniform constant electric field over a whole distance D. If it's not that way, then you can't use that. Okay, so just keep that in mind. Anybody have any questions on that one? All right, so example 3. We're going more on that paradigm thing. This one says, consider the capacitance of a coaxial cable whose inner wire has a radius. I don't know what happened to my U and my S. A radius RA, and whose inner radius, and whose inner radius of the outer wire is R sub B. In other words, R sub B is greater than R sub A. Use Gauss's law, delta V equals negative integral E dot dl, and C equals Q over V to compute the capacitance of a length L of the wire, assuming the inner wire is positively and uniformly charged so that a length L has a charge of plus Q, and the outer wire is similar but negative. Okay, so in other words, I'm doing that whole paradigm thing again. And I am also going to correct this to say radius. Okay. Now, what we're looking at is I'm going to draw a coordinate system just because it comes in handy. And I'm going to imagine, for instance, a cylindrical coordinate system, which helps me a lot more. So this is the x-axis, this is the y-axis, and this is the z-axis. And now what I'm going to imagine is I've got a inner wire whose radius is r sub a. And it goes on for essentially ever that way and essentially forever this way. Okay. In other words, I'm trying to go on the assumption that the wire is infinitely long, but we know it only means that it's only at least 10 times farther away from the end than I am from being next to it. And then outside of that is a concentric cylindrical shell. I'm showing its thickness just because it's a real object and it has a thickness, but the inner radius is the part that matters. And again, this goes on for infinity as well. I hate when this happens. Okay, so right here, we can imagine, again, this goes on for forever, but what I'm seeing in this diagram is this little distance from here to here is 2RA. And this distance from here to here is 2RB. Okay. And I'm going to say that this length right here from here to here is L. So I'm going to imagine a Gaussian surface like such. It's going to be a Gaussian pillbox again, only this time the soup label is the part that's going to have the electric field be a constant on it. Okay, and its radius is just going to be r. So applying Gauss's law, left-hand side, of course, my hypothesis is that the electric field is equal to some magnitude that only depends on r, the distance parallel to the xy plane, and points in let's say the r hat direction. This is sort of like the n hat that I did the last time, but specifically I called it r because I want to use the r from cylindrical coordinates. So that's from cylindrical coordinates, which I wrote so small that you can just barely see it, but it's from cylindrical. Okay. So the left-hand side of Gauss's law, the closed integral of E dot dA, becomes the integral over the top, which is E of r hat dotted with dA k hat plus the integral of E of r hat dotted with negative dA k hat for the bottom, plus the integral of E of r hat dotted with dA r hat, and this is over the soup label. Now, this is going to become the integral dot 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 r hat dot k hat, and that's 0. And that's the integral over the top. Then it's going to be integral dot 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 r hat dot k hat, and that's the integral over the bottom, and that's going to be 0 as well. And then the last part is going to be plus e of r times the integral of dA over the soup label of r hat dot r hat. In that case, it's r hat dot r hat is 1. Okay. So the left-hand side becomes E of R times the surface area of the soup label. So the surface area of the soup label is 2 pi R times L. Now the right-hand side of Gauss's law, Q enclosed over epsilon naught, we already found that lambda is equal to Q over L because it says a length L has a charge plus Q. Okay. So in this case, Q enclosed is purely lambda times L, which is just positive Q over epsilon naught. So I can say left-hand side equals right-hand side, and I can get E of R times 2 pi RL is equal to lambda L over epsilon naught. And what we find is that E is equal to lambda over 2 pi epsilon naught R, and it's going to point in the R hat direction. And I'll subscript that CYL, so we'll remember the cylindrical coordinate or the polar coordinate, either one. And that's the electric field. So now I have the electric field between the plates. Okay. Now inside, what we were told is this inner one has a charge of plus Q, and this outer one has a charge of minus Q. Okay. So now I'm going to take an integral to calculate delta V. So delta V is equal to the negative integral of E dot dL. Okay. Now what I'm doing is I'm integrating from the negative outer the inside of the cylindrical shell. I'm integrating from that, which is a distance RB away, to a distance RA away. That way I'm supposed to get a positive voltage. So the negative is part of the formula. The electric field is going to be lambda over 2 pi epsilon naught R hat. And then the DL is actually, this time, instead of using the DL to indicate the direction, I'm going to use the range of integration, and I'm going to say the DL is just the positive coordinate direction. So I'm going to call it dr r hat as my DL. And that's going to force me to say I'm going to integrate from RB, that's R equals RB, to R equals RA. Okay, and remember RB is greater than RA. So now I can say negative lambda over 2 pi epsilon naught integral of dr over r hat dot r hat, which of course is 1, and I'm integrating from RB to RA. Now, this is basically the integral of r to the negative 1 dr. The integral of r to the negative 1 dr is r to the negative 2, or excuse me, it's the natural log of r. So I can go ahead and evaluate this by saying negative lambda over 2 pi epsilon naught times the natural log of r, but I got to evaluate that at RB and RA. So this is going to be negative lambda over 2 pi epsilon naught times the natural log of RA over RB. Now, I used a property of logarithms there. The natural log of RA minus the natural log of RB is the natural log of RA over RB. Now, since RA is smaller than RB, then the natural log of that is the natural log of a number smaller than 1. So it actually gets you a negative. So the smart thing to do would be flip the fraction upside down, and I can then remove the negative. So I get lambda over 2 pi epsilon naught natural log RB over RA. Okay. Now I see that is positive. That's a good sign. We did everything correctly. Now I finally do the last part of the paradigm, which is C is equal to Q over V. The Q is actually equal to lambda L. That'll come in handy. And then the V, of course, is lambda over 2 pi epsilon naught natural log RB over RA. So ultimately what we get is the capacitance per unit length, which if you actually look on coaxial cable, that's the black cable that runs from your satellite dish or your cable box to your TV or to the outside anyways. That's coaxial cable. And sometimes it's printed on the outside what the resistance is per unit length and what the capacitance is per unit length and what the inductance is per unit length, but sometimes it's not printed on there. But either way, that's what it would tell you is capacitance per unit length. So that's why I solved for C over L. And what we see is that this lambda, which is a property of charge, not geometry, that lambda cancels out because our capacitance should only have geometric figures in it. So I end up getting that the capacitance per unit length is 2 pi epsilon naught divided by the natural log of RB over RA, and that's exactly the right answer. Anybody have any questions on that one? Okay, let's go ahead and take a 5-minute break at 6:49. Let's just be back at 6:55. I'm going to step away for a second, but I'll be right back, and then you can ask me questions when I come back. So I will see you at 6:55. Oh, it's okay.
Yeah, that's fine.
You put them in there?
Yeah, they're in your stock.
Okay, that's cool. I was talking to Fripper and Sean. Good in principle. Take a little map and all the things in your TV. Yeah, I feel like it over there. Actually, we can stack them top of each other and then put the whole thing under the TV. Anyways, I get back to my students. I'm back, everyone. We've still got 3 minutes, so take your time. But if you have any questions, I'm here if you need to. Can't tell you how excited I am. My friends came down and they got my bookshelves all fixed. Got the books up here. I'm looking at all my books. I'm so excited. All right, got about 1 minute left, everybody. All right, it's time to get back started. Does anybody have any questions about the last example we did? I'm trying to rapidly get into the swing of doing Gauss's law really, really quickly. So you'll know how to do it, because really, you really shouldn't be putting even as many steps as I did on this one's a little bit more than normal. You would maybe have the closed integral E dot dA equals, and then you'd have something showing that you're doing the integral over the top, the integral over the bottom, and the integral over the soup label. And then your very next line, or your very next equals, would be E of R times 2 pi RL. That's how quick that should go. So you need to get in the hang of that, because the left-hand side is supposed to be the easiest part. And it's always some area times an electric field strength. And the right-hand side, then you might have to integrate. That's the side where you might actually have to integrate. But other than that, it can be done with simply a ratio or something like that. So no questions? All right, well, let's show you another one. And this is the last one for me to show you the paradigm. So again, I'm using Gauss's law. So here's my solution. Now I need to have some kind of figure for you to understand this. So I'm again going to draw a coordinate system. There's my z-axis. There's my y-axis, say. And here's my x-axis. Now, what I'm going to do is I am going to draw a sphere like that. And now I'm going to draw another sphere like that. And I was trying to hopefully make sure the program would actually make it spherical instead of it looking like crap like it did. So it did. That's good. So this is a sphere. And this is the outer sphere. And of course, this radius is RB. and this radius is RA. Okay. Now I am going to need a Gaussian surface. Now I need a Gaussian surface on which the electric field is a constant. Should I use a soup can or should I use a sphere for this one?
Here.
Yep, because on a sphere, the electric field we know due to a point charge or a spherical distribution of charge is only related to the radius. So if the radius is a constant, the electric field is a constant. Therefore, the electric field should be a constant on any spherical surface. So I'm going to draw a Gaussian surface like that. And again, I'll let the program make it actually look spherical. Okay, so that's my Gaussian surface, and its radius is little r, which is between RA and RB. So my hypothesis is E is equal to E that depends only on R times R hat, but this time the R hat is for spherical coordinates. Okay. And actually, I really should do, y'all can see that that's coordinates with an I in between the V and the N. So that's that. Now I'm going to write my left-hand side. The closed integral of E dot dA is equal to the integral. Now, what we know is the inner charge is supposed to be positive Q. Right there. So I'm going to say the electric field is Q over 4 pi epsilon naught r squared, and it should point radially outward. Again, this is the this is the spherical coordinate. If you wanted to, you could subscript it with a SP for sphere. I don't really necessarily need that, but I'm saying you can do it. And now I'm going to dot it with dA, and dA is going to be just a dA times r hat. Okay, that's the nature of the spherical coordinates. You just have to do that, no problem. Now, because we're on the surface of the sphere to do the surface integral, then the Q over 4 pi epsilon naught r squared, all of that's an actual constant. So we can pull that out in front. So it's going to be Q over 4 pi epsilon naught r squared integral of dA over the sphere of radius r times r hat dot r hat, which of course is 1. So we ultimately are going to just get Q over 4 pi epsilon. Oops. Crap. Y'all realize what I just did? I got confused with my voltage. And, you know, the voltage step is where you put in the electric field. I just put in the electric field instead of deriving it. I apologize. Let me fix that real quick. That's two major mistakes. But anyways, so I got to use my hypothesis. So my hypothesis is E of R hat dotted with dA R hat. Sorry about that, everybody. Again, we're on the surface of a sphere of radius r, little r that is. So the E of R is a constant. So I get E of R times the integral of dA R hat dot R hat. And again, this is over a sphere of radius r. So the dA really just becomes the surface area of the green sphere. So the answer is E of R times 4 pi r squared, because that's the formula for the area of the surface area of a sphere. The left-hand side, or excuse me, the right-hand side. The right-hand side is supposed to be Q enclosed over epsilon naught. Notice I've got the entire inner sphere enclosed, so the charge is plus Q. So I'm just going to say Q over epsilon naught. And then I'm going to set left-hand side equal to right-hand side. And that's going to give me E of R times 4 pi R squared is equal to Q over epsilon naught. So E, using my original hypothesis, is just Q over 4 pi epsilon naught R squared R hat. So that's step one of the paradigm. I've got that done. Okay. Step two of the paradigm is to calculate delta V. So delta V equals the negative integral of E dot dl, where E is again, the conservative electric field. So the conservative electric field points outward. In fact, I just determined what it would be. And we're going to say it's negative integral Q over 4 pi epsilon naught R squared times R hat. All of that is going to be dotted. This time, I'm actually going to go from RB to RA again, just like I did last time. But this time, I'm going to use the DL to indicate the direction. So I'm going to say the direction is negative dr R hat. And now that means I have to go from small number to big number. So I'm going to integrate from RA to RB. And that's because I go from small number to big number if I'm using the DL to indicate direction. So that's what I've done. The two negatives cancel out, and I get Q over 4 pi epsilon naught integral dr over r squared times r hat dot r hat, but the r hat dot r hat is just 1, and I'm going to integrate from RA to RB. Okay, so the integral of r to the negative 2 is r to the negative 1 divided by negative 1. So I'm going to say it's negative Q over 4 pi epsilon naught. Now I have to evaluate 1 over R first at RB minus 1 over R at RA. Now RB is bigger than RA, so 1 over RB is RB is bigger than RA, so 1 over RB is actually smaller than 1 over RA. So this quantity in the parentheses is negative. But when you multiply it by the negative, it becomes positive. So I'm going to reverse the order and then make it a positive. So in doing so, I get Q over 4 pi epsilon naught times 1 over RA minus 1 over RB, which I can get a common denominator if I so desired. And when I did that, it would be Q times parenthesis RB minus, hold on a second. RB minus RA, because I'm going to multiply 1 over RA times RB over RB and 1 over RB times RA over RA. So I get RB minus RA in the numerator, and I get 4 pi epsilon naught RA RB in the denominator. So that's what my change in voltage is. Notice it came out positive like we wanted and all that good stuff. So now I'm up to the third step in the paradigm, which is C is equal to Q over V. So I'm going to take Q and I'm going to divide it by Q times RB minus RA over 4 pi epsilon naught RA RB. So ultimately, the capacitance because these Q's cancel out, the capacitance is going to be equal to 4 pi epsilon naught RA times RB divided by RB minus RA. And that's it. Anybody have any questions on that one? Okay, so that was the last one where I show the paradigm, but I still need you to have some sense of how to do how to calculate capacitance in general without all the other stuff. So this next step here is example 5, and it says estimate the capacitance per unit length of two very long straight parallel wires of radius r if one carries a charge of plus q and the other one carries a charge of negative q, assuming that they are separated by a distance d. Okay, so this is a good problem. In fact, they're talking about the old antenna wires, which none of you, I'm sure, are old enough to remember. But when I was a kid, before cable came out, we basically had, like, in some cases, you'd have a circle of metal like that sat on your TV, and it had a little knob, and you could adjust it, and the circle would go like this as you turn the knob. But the connector from that little circle antenna to the back of your TV was this clear plastic flat thing that sort of looked like those skate eggs that I heard they're called shark or skate eggs that you find on the beach. They have, like, they're a little fat little purse thing, and it's got 4 little weeds that stick out of it. That's what it looks like. But it was a clear flat wire that was clear plastic, and then in each side there was a wire in it. So that's what we're looking at here. I'm going to go ahead and draw a picture of it for you to better understand. What you can do is imagine a small wire right here and another small wire right here. And let's imagine for a second that the distance between them is d. Okay. And in addition to that, I'm going to imagine that their specific radius is in fact r. So I'm going to say this little radius is r and this little radius is r. Now, what I can do is I can realize that this left one is just like the Gauss's law that we did for a cylinder. So the electric field due to the positive charge, so I'm going to say this guy right here has a charge of plus q, and this one has a charge of minus q. And I'm going to imagine at a point right here where the distance is x from here to here. Okay. So I'm going to say the electric field at that point due to the positive charge is in fact equal to lambda over 2 pi epsilon naught times x. And that would be the actual electric field due to the positive side. Okay. Now, the electric field due to the negative one would be, now in this case, this is negative, and we're talking about at this dot right here. You can see that the positive charge is going to create, actually, let's put it this way. Is going to create electric field pointing to the right, and the negative charge is going to create a electric field pointing to the right as well, because the charge is actually the charge is negative, so a positive charge would be attracted to it. So in this case, I'm going to say again, it's lambda over 2 pi, only this time the distance is, I should say 2 pi epsilon naught first, hold on. And now the distance is going to be d minus x. Okay. So the electric field between along that line between them is lambda over 2 pi epsilon naught x plus lambda over 2 pi epsilon naught d minus x. So that's the total electric field between them. I need to now calculate the voltage difference between them. So delta V is equal to the negative integral of E dot dl. So the electric field is what I'm looking at here. So I'm going to put the negative out in front. The electric field is going to be lambda over 2 pi epsilon naught x plus lambda over 2 pi epsilon naught d minus x. And all of that's going to point in the I hat direction because I'm going to pretend like the right direction is the X direction. So I can do that after the fact by pretending that this is my X axis and this is my Y axis. Now, I want to go from the negative charge to the positive charge. That way I'll get a positive voltage. So I'm going to say dot this. And this time I'll use the range of integration to dictate the direction I'm going. So this is just going to be dx I hat for the dl. But I'm going to integrate from x equals d minus r to x equals just plain r. Okay. The d minus r is actually where I'm starting off at, and the R is the place where I'm ending at, because I really only need to know the difference between the inside edge of the wire and the outside edge of the other wire, or excuse me, well, yeah, the outside edges of the wire. So I can now do this, and I'm going to get negative lambda over 2 pi epsilon naught integral from d minus r to d, excuse me, to r, of, now I have 1 over x plus 1 over d minus x, all of that multiplied by dx, and then I hat dot I hat, which is just 1. Okay. So for the first case, the integral of x to the negative 1 is the natural log. And I'm going to get negative lambda over 2 pi epsilon naught. The integral of dx over x is just the natural log. So that's going to become the natural log. And then I'm going to evaluate that at r, and then minus d minus r, which gives you that. Again, I'm using the principle of logarithms that says log of a minus log of b is equal to the log of a minus b, or excuse me, a divided by b. Now this other one, I have to, for instance, assume that we let u equal d minus x, implies du is equal to negative dx. So I need a negative sign in front of that. I can do that by multiplying by -1 and then multiply by -1 again. And in this case, I'm going to put a minus in front of it. That'll compensate for the -1 I had to put in there. And now it's going to be the natural log of u, which is d minus x. So now I'm going to evaluate the natural log at of d minus x evaluated at x equals r. So this would be d minus r over d minus r. Okay. So that should be what we get. I can reverse the order of these to get rid of the negative in front of the lambda. So that's going to be lambda over 2 pi epsilon naught times, now I have the natural log of d minus r over d minus d minus r is just going to be positive r minus r over d minus r, excuse me, minus the natural log of r over d minus r, which is really convenient because the subtraction of logs is the same thing as the natural log of the division. So I'm now going to write this as lambda over 2 pi epsilon naught, and now I'm going to say this is the natural log of d minus r over r. Now, I want to divide it by r over d minus r, but that's the same thing as multiplying by the reciprocal. So if I do that, I can do d minus r over r times that, and that gives it to me. Oops, hold on, I lost something. That looks pretty good. Everything looks okay there, but yeah, that's right. Okay, so this is actually correct. I'm just trying to make it match what the book did. This is actually completely correct. So what we have now is delta V is equal to lambda over 2 pi epsilon naught times the natural log of d minus r squared over r squared, which you can realize that the natural log of x to the u power is u times the natural log of x. So I could actually get rid of that these exponents of 2 by putting them out in front of the lambda, but then that would actually cancel out the 2 downstairs. So that gives me lambda over pi epsilon times the natural log of d minus r over r. Actually, that's really terrible looking, so let me fix that a little bit more. So that is my actual voltage. Now, if the D is really a lot bigger than R, then D minus R is essentially the same as R. So I could also write lambda over pi epsilon naught natural log of D over R. Now, all of that's fine. That gives me a good result. That's approximately what it's going to be. Now I can go for the third step of my paradigm, which is C is equal to Q over V. We know the charge is just plain Q. So we're going to divide that by, well, actually, I should say the charge is lambda L since we got a lambda in there. So I'm going to say the charge is lambda L. And then I'm going to divide that by lambda over pi epsilon naught times the natural log of d minus, or excuse me, of d over r. Like that. And that gives me the capacitance per unit length is in fact equal to pi epsilon times the natural log of d over r. Oops, that part comes in the bottom. Sorry about that. So pi over epsilon naught times the natural log of d over r, and that should be the capacitance of that old school antenna wire. Ada asked for the steps, so numbering them and that sort of thing. paradigm. One, use Gauss or Coulomb to find E. Two, use delta V equals a negative integral E dot dl to compute V positive minus V negative. And what I mean by that is the voltage change in moving from the negative Q to the positive Q. So that the final one is the positive Q. That's why I said V positive minus V negative. And then step 3, use C equals Q over V for to get C. That's it. Does that help you, Ava? So the steps are use Gauss's or Coulomb's law. You're almost always going to use Gauss's law, but in principle, you could use Coulomb's law. You're going to use Gauss's law or Coulomb's law to find the electric field between the between the positive and negative plates or whatever they are. Then you're going to use delta V equals negative integral E dot dl to find the voltage difference between the negative plate and the positive plate. And you want to go from the negative plate to the positive plate so you get a positive. And then finally, you want to use C equals Q over V to compute the capacitance. Now, that's all the pure capacitance stuff until we start talking about dielectrics, which I've already hinted to. But now we got to go to something else. Okay, so this part right here, I usually don't do the derivation, or excuse me, I usually do the derivation, and this time I was actually thinking about not doing the derivation, but I realized that when I do the derivation, that's pretty much the only time you get to fully understand what happens to a capacitor when you connect it to a battery. So let me start off with the figure at the top left. You see that you have N capacitors. Notice the symbol for a capacitor is 2 parallel lines. It looks a lot like a battery, but the battery has one line that's long and the other line that's short. And the long line corresponds to the high voltage end, and the short line corresponds to the low voltage end. The capacitor just has 2 lines that are the same length, but sometimes it'll have like a bent line. That's another symbol for a capacitor. Or it'll have 2 straight lines, but it'll have a arrow drawn diagonally through it. That's another symbol for a capacitor. All those are symbols for capacitors. I put them on the first page. But what's going to happen here is when I connect this battery that you see down at the bottom of the circuit in the top left, the positive side of the battery is going to compel the positive charges in the wire to run away from it. So you can imagine little positive charges being compelled to move this way, and this way, right? That's going to force all the positive charges to build up on the side of the capacitor C1. Now, because that left-hand side is positive, all the positive sides, all the positive charges on the right-hand side of C1 are going to run away, and that's going to leave negative charges on the right-hand side. But originally, all this had 0 charge, so now all that positive charge is going to build up on the left-hand side of C2. That's going to cause a bunch of negative charge to build up the right-hand side, and again, and again, and again, we get the same thing. Okay? And ultimately, what happens is all the little positive charges come back to the battery this way. But once that total voltage, once V battery is equal to V1 plus V2 plus V3 plus ... plus Vn. Once that's the case, then the charges stop moving. They don't have any compulsion to do so anymore. Now, what we know is that the charge on the left is equal to the charge on the right, and we also know that the voltages add up to give the total voltage of the battery. Okay. Well, the total voltage of the battery is exactly the voltage on this equivalent circuit. So what we're trying to do is find one capacitor that I could replace all N capacitors with. The capacitance of that one capacitor would be C sub EQS, and the EQ means equivalent and the S means in series. So what I want is V battery, since C is equal to Q over V, then V is equal to Q over C. So what this means is Q total, which is how much charge left the battery, divided by C equivalent series. That's the voltage of the battery in this right-hand circuit. So in other words, that is what goes there by looking at that circuit. Okay. Now, what we saw is that a certain amount of charge, Q total, is going to leave the battery. That Q total is going to arrive on the left-hand side of C1, and then the negative of that Q total will be on the right-hand side. And then the left-hand side of C2 is going to have the same positive Q total, and the right-hand side will have the negative. So what we see is Q1 over C1 is plus Q2 over C2 plus dot 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 Qn over Cn. But in this case, Q1 is equal to Q2 is equal to Q3 is equal to dot 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 Qn, which I'm just going to call Q total. So all of that is equal to Q total over C equivalent series. So from that, I get 1 over C equivalent series is equal to 1 over C1 plus 1 over C2 plus dot 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 plus 1 over Cn. So that turns out to be the formula for equivalent capacitance in series. Now, if you think about the same thing for the circuit down here, what you see is immediately some little positive charges are going to be moving this way and this way. And in this case, some fraction of them, Q1, will go over to here, and I'll get positive charges here. That'll compel the negative charges, the positive charges on the right-hand side to leave, and they'll leave negative charges. And this will be Q1 as well. Now, on this case, it's going to be Q2. And Q2 over here. In this case, it's going to be Q3 and negative Q3 on this side. So what we have here is Q total is equal to Q1 plus Q2 plus Q3 plus dot 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 plus Qn. Okay. That's Q total, but we know C is equal to Q over V, so Q is equal to C times V. So looking at this circuit right here, we're going to get Q total is C equivalent parallel times V total, or excuse me, times V battery. That's going to be equal to Q1, which is C1 times V1, plus Q2, which is C2 times V2, plus dot 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 plus Cn times Vn, which is Qn. Okay. But they're all in parallel. So V1 is equal to V2 is equal to V3 is equal to Vn. Therefore, we reach the conclusion that C equivalent in parallel is equal to C1 plus C2 plus plus Cn. And that's the formula for when they're in parallel. Y'all remember from Ohm's law and your series and parallel labs that this is exactly the opposite of the formula for resistors. So hopefully that'll help you remember it, because you probably got the formulas for resistors down pat because you've discovered it in a lab. So when you have resistors in series, it's R1 plus R2 plus R3 plus blah, blah, blah is equal to the total R. When they're in parallel, it's 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3, blah, blah, blah. This is exactly the opposite. Anybody have any questions on that? All right, so let's work an example. So what I'm going to do is use these formulas to find the equivalent capacitance. Then it wants me to find the voltage across and the charge on each of the original capacitors. So here's my solution. Now I'm making use of those two formulas I just had. Now what I'm looking for is two capacitors that immediately fit the bill of being either in series with one another or in parallel with one another. You look and you can sort of see like, well, the 2 microfarad and the 3 microfarad, they're actually in series with each other. So that works okay. So what I'm going to do is I'm going to say 1 over 2 plus 1 over 3 is equal to 1 over C, and I'll call this 2, 3. So that's going to be the equivalent of the 2 and 3 microfarad capacitors. Now, we know that I can get a common denominator by multiplying the 1/2 by 3 over 3 and the 1/3 by 2 over 2. So this is going to be 3 over 6 plus 2 over 6 is equal to 1 over C23. And therefore I get that's 5 over 6. So C23 is equal to 6 over 5, which is really just 1 1/5. 5 goes into 6 one time, and then 1's left over. So this is 1.1/5 is 2. So this is 1.20 microfarads. So that means my circuit now looks like this. 1.00 micro. Notice I can leave off the F because the symbol gives the actual fact that it's a farad. This one's going to be a 1.20 microfarad. And now it's in parallel with a 4.00 microfarad. And then that's in parallel or in series with the 5.00 microfarad. And that's equivalent. Now I see that I have the 1.20 and the 4.00 in parallel. So now I can say C 1.24 is equal to 1.20 microfarads plus 4.00 microfarads, which gives me 5.20 microfarads. So now I have the equivalent of 1.00 microfarad in series with 5.20 microfarad which is in series with 5.00 microfarad. And of course, the equivalent here is the total equivalent. So I'm just going to call that C equivalent. And in this case, I get 1 over C equivalent is equal to 1 over 1.00 plus 1 over 5.20 plus 1 over 5.00. That's not very good. I hate that, right? But it's easy enough to just do with an actual calculator. So 1 over 1 is equal to 1. 1 over 5.20 is equal to 0.1923. And then 1 over 5 is 0.200 microfarads. So I'm going to say plus 1 plus 0.2. That gives me 1 over C equivalent is equal to 1.3923. Now, in principle, that's supposed to be 1 over 1. So that's 1 with two decimal places. The 5.20 is 1 over 5.20. So that should really be to 3 decimal places. And the other one should be to 3 decimal places. So basically, these two are not sig figs. And now I'll flip that over by raising it to the -1 power. And oops. I should have left off those units because it's technically not microfarads. But the main thing is I now get that C equivalent is equal to 0.718 microfarads. So that's the equivalent capacitance of all those. And I should underline this 2 here to make sure it's not. Now, to fix the other thing I did, let's just get rid of this microfarad and just put a plus there. And get rid of this microfarad. Okay, technically all those have units of 1 over microfarads, but the main thing is now I got that. So I now have the equivalent capacitance of all those capacitors. Now I'm going to show you how this comes into play with the other parts, because part B, they're wanting to know what are the voltages and charges across it. So what I've done is basically made an equivalent circuit that says, okay, I have this battery right here that is 12.0 volts, and it's in series with a capacitor that has a capacitance of 0.7182 microfarads. Okay. So the charge that's leaving the battery is exactly the same amount of charge that's leaving the battery in this situation. So I can get from this that Q is equal to C times V. Remember, C equals Q over V, so Q is equal to C equivalent times V. So the Q is going to be 12 times the 0.718 micro, so I get 8.619 microcoulombs, and that's Q total. Okay, so that's the total charge that leaves. Now I can look back at the original figure and realize that the amount of charge is 8.619 microcoulombs is what's leaving that battery. And in fact, that means the 1 microfarad capacitor call it C1, implies Q1 should be equal to 8.619 microcoulombs because it has nowhere else to go. And in fact, you can even do that for the 5 because if 8.619 microcoulombs leaves the battery, then 8.619 microcoulombs has to return to the battery. So you can now use that to conclude that the charge, that the charge on the 5 microcoulomb capacitor is also that same thing. So I'm now going to say C5 is equal to 5.00 microfarads, and this is going to, I call that Q1. So that means Q5 is going to be 8.619 microcoulombs. So now I've got the charge for 2 of the capacitors. Now what's going to happen is that 8.619 is going to go here. Some fraction of it's going to go to the top and some fraction of it's going to go to the bottom, right? But what matters is the voltage is going to be the same. Now, we could examine it in the original circuit, but it's a lot nicer if I look at it in this circuit where I say right here is 8.619 microcoulombs, and some of it's going to go to the 1.20, which is basically what's going to happen to the 2 and the 3 microfarad, and then the rest of it's going to go to the 4.00 microcoulomb. So what I can do is say that Q top, which means 2.00 microfarad and 3.00 microfarad, Q top is going to be equal to, in this case, it's the 1.20, to write this in red, is equal to the 1.20 microfarad times the capacitance, well, that's what I get, times 12.0 volts. So that's obviously 1.44, I think. 1.20 times 12 is 14.4. So this is equal to 14.4 microcoulombs. Now, the total was 8.619. Whoa, Nelly, hold on, what's going on here? The 6 works and the 5 works, that works fine. And then 6 over 5 is 1.20. Okay, so it's smaller than both of them, so that makes sense. And then, oh, I don't know that. I said 12 volts. That was stupid. I don't know why I did that. What we're trying to find here is what is Q top. So I know we got a little time left. So Q top is what we're talking about here. And the Q top is going to basically, well, let's put it this way. Q top plus Q bottom is equal to 8.619 microcoulombs. Of course, that's one extra non-sig fig. That's the main thing. Conservation of charge says if 8.619 comes into this junction, then the sum of what comes out must be 8.619. Now, the voltages are obviously the same, but the capacitances aren't. So what we have to do is figure out, well, what is the voltage? Well, voltage from C equals Q over V, voltage is equal to Q over C. those two voltages have to be equal. So that means Q top over 1.20 microfarads is equal to Q bottom over 4.00 microfarads. So this means that Q top is equal to 1.20 over 4.00 times Q bottom. So I can now plug this in and say 1.20 over 4.00 times Q bottom plus Q bottom is equal to 8.619 microcoulombs. So I can solve for that and find out that Q bottom is equal to 1.2 divided by 4 is equal to 0.3. So I've got 1.3 times Q bottom is equal to 8.619. So I need to take 8.619 and divide it by 1.3. Uh, 8.61, excuse me, coulombs, not farads there, over 1.3. And that is going to be equal to 6.630 microcoulombs. So that's Q4 is equal to 6.630 microcoulombs. I can box off that one now. And the other one is the Q top. And of course, the way Q top does is Q top goes to the left-hand side of the 2 microfarad capacitor, and then the negative of that appears on the right-hand side, and then the positive of that appears on the left-hand side of the 3 microcoulomb. So we can now say that Q top is equal to Q2, which is also equal to Q3, which is equal to 8.619 microcoulombs minus 6.630 microcoulombs. So I get 1.99 microcoulombs. So I'm going to write this here. Q2 equals Q3 equals Q top equals 1.989 microcoulombs. So I've now got that. That's 1, 2, 3, 4, 5. I've now gotten all of the charges. The voltages are just found by V1 is equal to Q1 over C1. V2 is equal to Q2 over C2, dot, dot, dot. I didn't finish it because I didn't do the rest of those, but that's all you have to do to finish the rest is just take the charges that I found for Q1, Q2, Q3, Q4, Q5, and divide it individually by the C1, C2, C3, C4, C5, and you'll get the voltages. And that's it. We're done with what we're covering today. I ran 1 minute late. Hopefully that's not too bad for you guys. Don't forget, you have a online test that'll be due Monday or Tuesday. You'll see the date when you post it. And you have a face-to-face test that's going to be done due Tuesday or Wednesday. Again, you'll see that when I send out the email. But you guys are free to go, and I will wait here until the last person leaves in case anybody has any questions.
Hey,
Yes.
I had a quick question about the problems we were doing. So I understand the process of using Gauss's law in the integrals, but is there a simpler version? Because I'm kind of getting lost in the weeds. Like I understand the steps, but I'm getting a little stuck.
So I would say you could look in an algebra-based textbook, like the course that we're teaching here for 201 and 202. There's students running around that are taking that right now. They have the book that we use for that, and that actual explanation that they use for Gauss's law and that might actually help you a little bit. If you want to, let me do this. Let me stop sharing for a second. I don't know if I have one. I have all my books here.
It's not really the calculus. It's more of like the um, setting up the integrals the right way. Because like with the different shapes, how to set up each one.
Gotcha. So is it Gauss's law or is it Coulomb's law that's giving you the problem?
I thought, does the process work for both?
Yeah, so the difference being with Gauss's law, you're looking like you're doing this really fancy integral on the left-hand side, but you're really just getting the area times electric field, and you're using a very specific shape. It's got to be a sphere or it's got to be a soup can, right?
Okay.
Whereas when you're doing Coulomb's law, you have to compute that RP vector, the vector that points from the origin to the point at which you wish to know the electric field. That's called a vector RP. And then you got to compute the RDQ vector, which points from the origin to the little bit of segment of charge that you need that's actually causing the little bit of segment of the electric field. And then you got to compute RP minus RDQ. And then you got to compute the magnitude of RP minus RDQ. So that multi-step process normally is what gets people, just because it's multi-step. None of the steps are really that hard, but because there's so many steps, the students normally just get overwhelmed and don't do anything.
Yeah, I can definitely feel that. Like
Yeah, you feel
starting
like
the
you just get
process and then
started, can't you?
yeah, yeah, totally. I'll like look at it. Like I'm looking at one right now, and it's just like a little. I'm looking at the one we did in class. And
Is it for the
yeah,
infinite
it's like
line charge, the infinitely long line?
it was I'm looking at the two cylinders, one with radius RA and RB.
Okay, gotcha. So yeah, that's the actual Gauss's law one. And with this one,
Hmm.
what you say is, okay, let's simplify it and make it something simpler. So I've got two cylinders. According to Gauss's law, I have to integrate over a closed surface, and I need to choose a Gaussian surface. I've only got two sort of three choices of which Gaussian surface. So given that you have a coaxial cable like you saw in the drawing, do you think the Gaussian surface is going to be a soup can or a sphere?
I think it's a can because I'm kind of imagining it wrapping around the sphere or the
Around the cylinder.
cylinder.
Yeah, exactly. And you see that the electric field will point radially outward from that inner wire, right? So the inner wire may be going this way. So the charges are assembled all along this straight line. So a positive charge right here is going to cause the electric field pointing that way, but also pointing that way, but also pointing this way, but also pointing
Around the circle.
right. Notice
Okay, all right.
that is perpendicular to every part of that soup label.
Yes. Yeah, it's like along every part of the surface, you're going to have an electric field. Yeah, like you said, perpendicular, no matter where you are.
Yeah, and it's related to how far away you are from the wire, but since your soup can is concentric with the wire, all of the soup can label parts are the same distance away from the wire, so the electric field is going to be a constant on it too.
Okay.
Does that make sense?
Yes.
Now, when you look at the top and bottom of that soup can, the very middle of the top of the soup can is going to be at R equals 0. So the electric field is going to be infinitely large there, and it's going to get smaller and smaller and smaller the farther you get out. But the electric field is pointing again perpendicular to the soup label, whereas the dA has to point up for the top of the lid.
And then that's just a variable we use. It's not like we're integrating with respect to A.
A being an area, yes.
Okay. Okay.
And we've defined the dA vector to have a magnitude equal to dA, but a direction that's perpendicular and pointing out of the closed surface. So the dA for the
Okay.
lid points up, which happens to be perpendicular to every direction in the soup label, right? The soup label has all these directions, but the dA has that direction, and the dot product between that direction and any of these is 0.
Okay. What about the bottom? Is it the same thing?
Same thing, the bottom has a dA pointing this way, but again, the electric field and the soup label perpendicular all points that way. They're all at 90 degrees, so you get 0 for that one as well.
So that's why the top and the bottom don't matter with respect to the integral.
Exactly. Now,
Okay, you're just integrating along this sides.
exactly. You're doing the integral everywhere, but luckily it went to 0 for the top and bottom. Now that was just the opposite of when we did the plane, where the electric field was a constant on the top and a constant on the bottom and perpendicular to the bottom and perpendicular to the top. So we got an actual EDA for the top and an EDA for the bottom. But around the sides, the electric field was pointing this way or this way, which is always perpendicular to the soup label. So in the case of the plane, we actually had the soup label gave us 0, and the tops gave us E times A. The top and bottom gave us E times A. Whereas in the cylinder, the top and bottom gave us 0, and the soup label gave us E times 2 pi R L.
And then on the sphere, it's just the entire surface is constant.
Exactly.
Okay.
Okay.
Okay, that makes more sense.
So once you've limited it down to 3 possible Gaussian surfaces, really just 2, but 2 of them are weird, are acting differently than each other. Then it's just a matter of piecing that together. And it really is a lot of just memorizing exactly what I did in the 3 types of examples you saw and just repeat that over and over again. And eventually you're gonna figure it out enough where it'll make some sense. If it doesn't, it's okay. You still had it memorized, so you know exactly what to do.
Yeah, that makes sense. And then for the last test I prepared by just doing the practice over and over again, and I don't think it worked out as well as I would have wanted. Is there any other things that people do to prepare for these tests?
I would say what I think is absolutely necessary is that you completely understand every example in the chapters that are covered, unless it's an example
Okay,
from a section I skipped.
so use those problems in addition to the practice test, not just the practice test.
Yeah, because really, if you can't do those, you're probably just getting lucky by doing the practice test when you get it
Yeah,
right.
because there was a point where it's like you kind of memorize the practice test and you're not really applying the stuff.
Right. So I would say as a low standard, first make sure you can get through and like you can actually copy down or take a picture of just the question in the example. And then with your phone looking at that question, work that out from start to finish. If you can't do that, you don't understand that example well enough.
Okay, that
And,
makes sense.
and I would say stick to the last 2 chapters, which are covered on this coming face-to-face test. Stick to those last two chapters because you probably understood the previous 4 chapters well enough that you can get through it, whereas these last 2 are a little more pressing.
Yes, I would say that. Yeah, the thermodynamics I struggled a little bit, but I think that's because I didn't fully understand the meaning of each laws, and then
Right.
it was only afterwards where it kind of made sense, like what each one does. But
Right.
I'm looking through the problems now. I see the examples, and then like it looks like they show you how to work it out. I should just start with the top part and then scroll down when you're ready.
Yes. So see if you can do that with those examples in those 2 chapters. If you still need more practice, you can look at examples, but that's not nearly as helpful as something like this. So Physics for Scientists and Engineers is Sean's outline, and they have an E version that you could get if you wanted. Some libraries have them, so you can check them out as well, but they're really dirt cheap. And basically they have an example chapter that's just like each chapter in your book. So if you wanted to look for Gauss's law, for instance, I can flip through here and I see the kinetic theory of gases. I see thermodynamics, first law of thermodynamics, second law of thermodynamics, electric fields. So you can see here's all the worked problems for electric fields for all sorts of combinations. And then you go, and there's a chapter on Gauss's law, but look how
The
short.
work looks much more detailed than the
Exactly.
worked out looks much more detailed. Yeah.
Yeah, so the chapter synopsis is really short. It's a couple paragraphs, so it's easy to read, and then it's just packed full of examples where they work it out in detail.
Mm-hmm. Okay. Yeah, that looks helpful. Is that something I could find in the library?
The library, I used to have one on loan to them, but they eventually said, okay, nobody's been checking it out. You might want to come get it. So that's where this came from. But they can get it from another library, anyone that has it, or like I said, you can get it through Amazon, and it'll like come to your Kindle app instantly.
I'm
But
sure there's multiple editions of that kind of thing, though.
yeah, there's Physics for Scientists and Engineers is the one that you would want to cover the calculus base. And when I bought this, it was $15.95.
Okay, yeah, I'm sure I can find somewhere. That looks, I like it's all worked out much more detailed in the book.
Yep. And
Yeah.
they've got, if you look on the back, it's got titles of all the different versions you have, but look for university physics or physics for scientists and engineers. Those are the code words to know that it's calculus based.
Mm-hmm. And then the deadline for chapter 24 homework, I see that online as the first. Is that going to be moved back like the 23rd?
Yeah, I think today I moved it back to the 15th, if I remember correctly.
Oh, okay. All right. That's a good chunk of time.
Yeah, give you
All right.
plenty of time on
All
that
right.
one, 'cause we're just going through chapters 21 and 22, which is Gauss's law, of course, on
Mhm.
this. So, yep. I would definitely look into that Shahm's outline. And in fact, all your courses, there's going to be like statics, dynamics. They have a Shahm's outline for them. Even like C++, there's a Shahm's outline for that. Calculus, there's a Shahm's outline for that. Pre-calculus, there's a Shahm's outline for that. So they really are great.
Mhm.
But it's old school. I like books. A lot of people just rather go to Khan Academy. The problem with Khan Academy is unless you force yourself to listen to exactly what problem they're solving and then pause it while you solve it yourself, then you're just watching people solve problems. That's not nearly as
Mhm.
helpful as you figuring out how to solve the problem yourself. Even if you get it wrong 20 times, you're doing better for yourself.
Mhm. Mhm. And then this will be edited out of the recording, right? Like talking about tests and stuff.
Yeah.
Okay. All right. Cool. All right. Have a good holiday.
You too. Send me a text if you find any problems or something like that, or if you want me to look over something that you did to see if you understand how to do Gauss's law or Coulomb's law. Just take a picture of what you did, write it up as neatly as possible so I can read it, send it to me, and I can tell you what's going right or wrong.
All right. Cool.
All
Thank
right.
you.
Have a good one, Ethan.
Thank you. Bye.
You're welcome. Bye bye.